All right, so we've looked at a bunch of different types of reactions. What we're going to do now is take things a little step further, okay? So sometimes in certain reactions, when we look at the balanced chemical equation, there's a lot going on. But sometimes that is not always how the chemicals are reacting. Some chemicals do react, some chemicals don't. And what we're going to look at in this example is developing a net ionic equation. A net ionic equation is the bare bones of what is reacting. It is showing us what molecules are changing, and it eliminates what molecules are not changing. Okay. Now, net ionic equations only work for single and double replacement. So if we see a single or double replacement, we can do a net ionic equation if it asks for it. In this example, it says write the balanced chemical equation. Then it says write the total ionic equation. And then it says write the net ionic equation, okay, for the following reaction. The reaction is between potassium iodide and lead nitrate. I have chemicals that are composed up of two types of atoms or compounds. So I've got an ionic compound here, an ionic compound here. When two ionic compounds react, we have double replacement, okay? So to start, I'm going to write my balanced chemical equation, which is what I've been doing in all of the last lesson for the following reaction. Potassium iodide, ionic compound, I've got K plus, I minus. When I drop and swap, they cancel out. Okay, so I write Ki, and this is aqueous. Okay. I'm reacting this with lead 2 nitrate, NO3 minus. So I'm going to put Pb, I drop and swap, bracket NO3 2. This is also aqueous. Okay. Then I'm going to put my arrow. This is a double replacement reaction, so the metals are going to flip. So potassium is going to flip with Pb. So I'm going to get K plus and NO3 minus, which makes KNO3. Charges cancel. That is aqueous according to my solubility table. Heads up, anything with NO3, always soluble. Okay, NO3, always aqueous. Anything with that is always aqueous. Okay, you can put that in your notes. And then lead is going to go with iodide, 2 plus with I minus, Pb, I2. In your solubility tables, guys, this is solid, which we call a precipitate. Okay, so this is my chemical equation. However, it is not balanced yet, so we have to do that. So let's take a look. I've got one potassium here, one potassium there. Great. One iodide here, two iodides here. Okay, so I can change this one. I can put a 2 here. Well, if I put a 2 here, I now have 2 Ks, so I got to put a 2 in front of this. Well, that gives me 2 NO3s. Oh, look, 2 NO3s. So we're done. Okay, so I've done the balanced chemical equation. Now what I have to do, ladies and gentlemen, is I have to go to the total ionic equation. The total ionic equation is where we dissociate anything that is aqueous. So we break down anything that is aqueous into its ions. So I'm going to break down Ki, I'm going to break down PbNO3, 2, and I'm going to break down KNO3. I will not break down PbI2 because it is a solid, and solids are untouchable. So if I break down Ki, I'm going to get K plus and I minus. They were aqueous, so they're going to stay aqueous because they are dissolved in water. Well, how many K pluses, ladies and gentlemen, were here? Well, there were 2 Ks, so the 2 is going to follow. I can't just drop the coefficients, okay? There was 2 Ks, and there were 2 Is, so the 2 stay, okay? Well, now I can break down PbNO3, so I'm going to write Pb has a charge of 2 plus. Again, we're writing charges, guys, because the total ionic equation, the I means ions, okay? It was aqueous, it's gonna stay aqueous, and then I've got NO3, but how many NO3s are there? Well, there's one here, but subscript 2 means that there will be 2 there, okay? Then I'm going to put my arrow because this is my reactants. On my product side, I've got K again, K plus, stays aqueous, dissolved in water, and NO3 minus. Okay. And if you guys look at the coefficient, there was a 2 here. So there's got to be a 2 here and a 2 here. And last but not least, ladies and gentlemen, I have to write PbI2. Why? Because it has not changed. It's a solid. It's going to stay a solid. Okay. So I've written my total ionic equation. I have written every ion that is present in my reaction. All I did, guys, again, anything that is aqueous means dissolved in water. And we know that ionic compounds, when they go in water, they dissociate. Okay, so an ionic compound in water, H2O, dissociates. Dissociates means it produces ions, which we write in step 2. Okay, so all I've done is break down all of these. So now what I recognize, guys, is on the left side and the right side, I have some chemicals that are the same. If I have the same ions on the left and right side, they haven't changed. If they haven't changed, they have not reacted. So what chemicals have not changed? K plus didn't change. NO3 minus didn't change. So these right here, guys, I'll write it right here. The ones that do not change are called my spectator ions. Spectators, they sit on the bench. I'm sure you guys know some of your buddies that play on the basketball team that don't really get many minutes, right? I'm thinking of Kieran, but I could be wrong. We call them spectators, okay? So the spectator ions, guys, are going to be K plus. The 2 is irrelevant. I just care about the chemical. K plus and NO3, comma, NO3 minus. Those are my spectators, okay? They don't do anything, so I can get rid of them. Since they don't do anything, and I can get rid of them, I'm going to rewrite my net, my final reaction. Well, I've got 2I minus. That changed because it became over here. Pb2 plus, and that's going to produce PbI2 solid. And this, ladies and gentlemen, is my net ionic equation. Iodide ions, lead ions are going to combine to produce a new chemical, lead iodide. Okay? Potassium and nitrate do not change, so they are not necessary in our final net ionic equation. This, guys, represents what actually reacted.